There are situations where we're undertaking statistical modelling where a normal distribution will not be appropriate for our data. So we might end up with binary data where we go down the logistic regression route, or we could have count data that's not well approximated by a normal distribution. And in this situation, it may be that the Poisson distribution provides a good description for our data. So if we take a look at an example where we've got data on the number of failures for some equipment, and this equipment can be operated in two modes. So what we have for the equipment in our data set is a record of the amount of time spent operating in each of the two modes and the total number of failures that are recorded. So I'll load in our data and look at the first few rows of the data, so we can see we've got times for mode 1 and mode 2 operation and the total number of failures. So we can take a look at a scatter plot matrix using the lattice package, and this will give us an idea of relationship between the variables, the number of time in mode 1 and mode 2, and the total number of failures. So we can see that there's an increase based on both of those variables in terms of the total number of failures. The GLM function for generalized linear models allows us to fit models where we have a distribution other than a normal distribution for our data. So we specify our response variable, our y, number of failures, against a model including terms for the two modes, the amount of time in those modes, and an interaction between those modes by the asterisk. What we then also need to do is we set this argument here, family equals Poisson, to indicate that we Poisson distribution to our response. So I fitted that model, produced a summary, and we get a standard output. And we've got our table of coefficients, which indicates that there isn't an interaction. There's unlikely to be an interaction between the amount of time spent in the two modes and the total number of failures. So what we can do then is update our model by removing the interaction, producing the summary. So the update has the name of our model and then a command here which says we want to keep the same y variable, the same total model, but we want to subtract the interaction, and the colon indicates the interaction only. So we see here now we've got a simpler model, and here it's suggesting that the amount of time spent in mode 2 doesn't have a relationship to the total number of faults, but the time in mode 1 does. So we'll simplify our model further by removing mode 2 from the model, and we end up with our total response is related to the amount of time spent in mode 1. So then we can look at our diagnostics, and for a model with this number of data points, the various diagnostics don't suggest any major problems with this model. So last up, if we wanted to do some predictions from this model at particular times of operation from mode 1, make use of the predict function. So we specify the model we're predicting on and the new data. So we've selected a sequence of times in mode 1 from 30 to 140 minutes, going by a step size of 10. And we use type equals response so that the response is transformed back to the original scale for our predictions.